Welcome to today's paper reading. Today's paper is titled, RAT, Retrieval Augmented Thoughts Elicit Context-Aware Reasoning in Long-Horizon Generation. This paper was published on the AR14 preprint by Zihao Wang and colleagues from Peking University, University of California, Los Angeles, and Beijing Institute for General Artificial Intelligence. The abstract discusses a method for improving large language models' reasoning and generation abilities in long-horizon tasks. This method, called Retrieval Augmented Thoughts, RAT, involves iteratively revising each thought step with relevant information retrieved from the task query and past steps. This approach significantly enhances performance across various tasks, including code generation, mathematical reasoning, and creative writing. For instance, it improves code generation by 13.63%, mathematical reasoning by 16.96%, and creative writing by 19.2%. Additionally, it mitigates hallucination issues commonly found in these models. Large language models, LLMs, have made significant advancements in natural language reasoning tasks, particularly when combined with large-scale models and sophisticated prompting strategies like chain of thought, COT, prompting. However, there are growing concerns about the factual correctness of LLM reasoning, including possible hallucinations in model responses and intermediate reasoning paths. This issue is particularly significant in zero-shot COT prompting and long-horizon generation tasks. To address this, the authors propose a strategy called Retrieval Augmented Thoughts, RAT, which synergizes Retrieval Augmented Generation, RAG, with long-horizon reasoning. The RAT strategy aims to alleviate hallucinations in the intermediate reasoning process by incorporating outside knowledge. It employs a progressive approach where LLMs revise their reasoning step by step, similar to human reasoning processes during complex problem solving. Figure 1 illustrates the pipeline of Retrieval Augmented Thoughts, RAT. The process begins with a task prompt, denoted as I, which is used to generate initial step-by-step thoughts, 1, 2, by an LLM in a zero-shot manner. These thoughts may contain flaws due to hallucination. RAT then iteratively revises each thought step, -1, using RAG from an external knowledge base, referred to as library. This progressive revision ensures that each step of reasoning is informed by the most accurate and relevant information, significantly improving the quality and reliability of the generated output. The Retrieval Augmented Thoughts, RAT, method aims to support long-horizon reasoning and generation while mitigating hallucination when using large language models, LLMs. This is achieved by combining two indispensable ingredients: retrieval of factual information and the use of chain of thoughts, COT, for intermediate steps. However, a naive combination of these two methods does not necessarily yield improvements. The RAT process involves generating initial zero-shot COTs based on the task prompt, retrieving relevant information, and iteratively revising each thought step with the retrieved content. This iterative process ensures that each step of reasoning is informed by the most accurate and relevant information, significantly improving the quality and reliability of the generated output. Figure 2 illustrates the performance of various large language model, LLM, reasoning methods on creative generation tasks. The top part of the figure highlights examples where red text denotes errors or hallucinations in the text generated by LLMs, while green text indicates correct generation. Methods without Retrieval Augmented Generation, RAG, often produce incorrect information due to hallucination. Classical RAG methods, while highly related to retrieved content, tend to have a loose structure. In contrast, RAT-generated text exhibit the best performance in terms of accuracy and completeness. The bottom part of the figure provides a quantitative comparison of different LLM reasoning methods across complex tasks such as embodied planning, mathematical reasoning, code generation, and creative generation. The results clearly show that our RAT method outperforms all the baseline methods on every task, demonstrating its superior effectiveness. The experiments were conducted across 4 groups of benchmarks: code generation, mathematical reasoning, creative writing, and embodied planning. For code generation, benchmarks included Human Eval Plus, MBPP, and MBPP Plus. Mathematical reasoning was evaluated using GSM-8K, and GSM hard datasets. Creative writing and embodied planning tasks were assessed in open-ended environments like Minecraft. Evaluation metrics varied by task type. For code generation, PAS-K was used, while mathematical reasoning employed accuracy metrics. Embodied planning tasks were measured by executability and plausibility. The results show that RAT consistently outperforms other methods, achieving significant improvements in PAS-1 and PAS-5 rates for code generation. In mathematical reasoning, RAT demonstrated an average improvement of 18.44% on the GPT 3.5 model, highlighting its effectiveness across diverse tasks. Table 1 presents the code generation results across various benchmarks under zero-shot settings. The RAT method demonstrates superior performance compared to the direct method, showing significant relative improvements in both PAS-1 and PAS-5 metrics. This consistency in performance is observed across different base models, indicating the robustness and effectiveness of the RAT approach in enhancing code generation capabilities. Table 2 presents the evaluation results across mathematical reasoning, creative writing, and embodied planning tasks. For mathematical reasoning, RAT demonstrates significant improvements, particularly in GSM-8K and GSM hard benchmarks. In creative writing, RAT achieves a high win rate of 81.01%, outperforming other methods. For embodied planning, RAT shows substantial enhancements in executability and plausibility, with a 42.78% improvement over direct. These results highlight RAT's effectiveness in diverse tasks, leveraging iterative refinement and dynamic knowledge retrieval. Table 3 presents a comparative analysis of the impact of different retrieval strategies on the performance of Retrieval Augmented Thoughts, RAT. The table highlights that RAT significantly outperforms both the baseline and the COT plus RAG method in terms of PAS-1 and PAS-5 metrics across the Human Eval and Human Eval Plus benchmarks. Specifically, RAT demonstrates an 8.7 percentage point increase in PAS-1 and a 7.9 percentage point increase in PAS-5 over the baseline in the Human Eval benchmark. These improvements underscore the effectiveness of RAT's retrieval strategy, which iteratively refines queries based on evolving reasoning thoughts, ensuring the retrieval of highly pertinent information and significantly improving the quality and accuracy of the final generated outputs. Table 4 presents an ablation study comparing the impact of causal versus non-causal reasoning on the performance of RAT. The study reveals that causal reasoning enhances the PAS-1 metric by 13.2%, while non-causal reasoning increases it by 10%. Both approaches demonstrate substantial improvements in the PAS-1 metric, indicating the effectiveness of each reasoning strategy in enhancing RAT's performance. In the realm of retrieval augmented generation, RAG, recent studies have shown its effectiveness in enhancing the performance of large language models by guiding their generation process with retrieved knowledge. This approach is cost-effective as it avoids expensive and potentially unstable model parameter updates. RAG has been successfully applied to various downstream tasks such as code generation, question answering, and creative writing. Some recent works have also integrated reasoning to further enhance RAG's performance. For instance, methods like IRCOT, IRGR, GEEK, and ITRG have been developed to improve retrieval and reasoning capabilities. However, these methods typically use a single query for question answering tasks, whereas our proposed RAT method employs reasoning and draft answers in an autoregressive manner, significantly enhancing RAG's performance across various tasks. Additionally, advancements in reasoning within language models have led to notable methodologies since the introduction of chain of thought, COT. Innovations such as least to most prompting, zero-shot COT, and self-consistency have been developed to improve the reasoning abilities of language models. More complex frameworks like selection inference and tree of thought have also been introduced to expand reasoning paths. However, our RAT method differentiates itself by using RAG to access external knowledge that aids the language model's reasoning process. In this conclusion, we summarize the key aspects of Retrieval Augmented Thoughts, RAT. RAT is a zero-shot prompting strategy that combines chain of thought, COT, prompting with Retrieval Augmented Generation, RAG, to tackle long-horizon reasoning and generation tasks. It demonstrates significant advantages over traditional methods like vanilla code prompting and RAG. However, RAT has several limitations. Firstly, its performance heavily depends on the base large language models, LLM, capabilities in chain-of-thought reasoning and in-context learning. Secondly, the effectiveness of RAT is contingent upon the quality of the retrieved knowledge. Lastly, RAT follows a step-by-step reasoning approach, which may not always be optimal. Future research could focus on fine-tuning weaker LLMs to enhance RAT's performance, improving the quality of the knowledge base for retrieval, and exploring more sophisticated reasoning methods for LLMs. Thank you for watching.